I'm glad that we're live because the opposite alternative is closed. Give me a chance to start. There's no harm in you also recording from a Hangouts point of view. Let me you'll let me know when to start capturing. I can always trim.
Yeah, we're capturing, so we're good. You can start whenever you're ready.
Are you ready?
Three. It'll do a 3, 2, 1. We're live.
All right, wonderful.
Everyone, welcome to the it's in kind of like I'm Mike Hoffman. I work for I'm really lucky to have anyone interested, there's a free Wi-Fi afterwards, and then a board back there. So you can connect and that I'll be able to run it. We use the CPI. Hey guys, thanks Mike. Thanks for being here. Happy to talk about value and what we do for communities and for you. So we're a software. Traditionally, load balancers have been appliances, dedicated boxes with big box or big what we've done is sort of decompose the load balancer into control plane, and then the big one. And then the core looks a lot like after they dedicate themselves on software that can be deployed on their server with future staff. Oh. Exactly. So we particularly load balancer. Those are appliances. Decompose them into control plane and data plane. The control plane looks a lot like your capacitor, your Kubernetes capacitor. The data plane is software, and it can run on bare metal servers. It can run as virtual machines. It can also run as graphic. And what this allows us to do is it allows us to provide a lot of high performance traffic management and load balancing. We recently scaled the AVI software in a few minutes to about 1 million SSL transactions per second. That's a lot of performance, more than what most applications do. The point is not that you can do this. The point is that it's elastic. That means you can do it when you want to do it. And that makes sense for a lot of different types of things. In specific to Kubernetes and OpenShift, we work exactly the same way in both these technologies. And we'll see how some of that works. So if you have a Kubernetes cluster or a OpenShift cluster, at the beginning you would bring up and deploy the AVI controller, just like your Kubernetes cluster. And once you've done that, the AVI controller automatically discovers all the Kubernetes cluster. It will also bring up a data plane on everything. And this can be a Docker container, it can also be deployed as a Kubernetes pod. one pod per node, and this provides all the traffic management and all the services that we do for that. And then you would create a deployment. You would create a service corresponding to the deployment in Kubernetes, and the controller automatically synchronizes that and will create a corresponding what we call a virtual service in the app space. And these virtual services are actually provided by this group of red boxes here, what we call as the service. And as you scale the number of pods of service up or down, it automatically keeps track of that. It also manages the full life cycle of the entire service. And now you can also deploy this with across two regions, two clusters, if you want to scale your application across multiple regions or multiple clusters. We do that via what is called as JSON or the global service load balancer. And as traffic starts passing through this, you'll also see that we collect a lot of metrics, logs, analytics, which we make available to you. I'll do a demo in a couple of minutes, and you'll see the power of what you can actually utilize about your application with traffic. So how does it work? Now in this picture, I'm actually showing two clusters deployed across two regions. A user, like as usual, does a lookup of the application FTDN, and the JSLB service returns one of several virtual IP addresses. It can come from one of several clusters, depending on policies like the location of the user or the availability of the actual applications across these clusters or load on these clusters. And once the IP is returned, then the user actually connects to the IP to all the pods. We can also replace with proxy. So in this scenario, it works exactly the same way, except the actual client is another pod. So the pod requests the other service that it wants to target by name, which it gets an IP address corresponding to that. It then connects to that IP address, and then we get load balanced to all the jobs. So what this allows us to do is provide traffic management, routing, both within the cluster, across clusters, east-west traffic management. We are with a 7 load balancer, we can do it. And a lot of other enterprise class features. Our customers include a lot of banks, e-commerce, service providers. And as they move a lot of their legacy applications onto Kubernetes, a lot of these applications are not cloud-based. They were written for 5 years or 10 years with a lot of features and functionality and assumptions from outside of that. And that's where we come. We provide almost all the features that these applications need when they actually move from a VM or a form factor into Kubernetes or Yaml. So let me just stop here for a second and any questions before I actually go ahead and do that. Okay. All right. So there's going to be sort of 3 screens here. There is a Kubernetes cluster, which has just one demo cluster about 3 or 4 nodes. It's totally empty now, nothing happening with it. And then this is a screenshot of the ARI controller. And then this is just a simple UI that allows me to actually walk through this demo with steps. So in the first step, I'm actually going to configure a cloud on the ARI controller. As part of that, we provide the Kubernetes masters access information, IP, access credentials, and so on. Once we do that, then the ARI controller automatically discovers the cloud. It installs itself inside the cloud. That is, it spins up a data engine on everyone. So at this point, it's bringing up all the service engines in this cloud, and once we start up in about few seconds if the cluster is ready for taking traffic. Next step is I need a DNS service for mapping the application name to IP. So this is what I'm going to do, create a DNS service. And once I have done that, then I'm going to actually start creating some application. Right now, the only service that's running here is the DNS service. So I'm going to go ahead and create some applications. And we'll soon see there's some applications that begin to appear in Kubernetes. So we try to style these applications as a microservice, cloud native microservice-based applications. Doesn't do much. It's got a front-end application about that service photo, which talks to a few backend apps, which talks about backend apps as well. So the point is just to show how you would actually create using a cloud gateway. So the applications are beginning to come up now. Here that are still coming out. In a few seconds, they'll come up, and you'll see that as we create these applications, they will corresponding services will show up in Audi. And as part of that, we'll allocate virtual IP address for them. We'll drop in a DNS record for them. And regardless of where you run, you could run this in AWS, you could run GCP, you could run Azure. We'll do all of that, and you can point us to, okay, I have my own DNS system for bots. We can work with that, or it's not or something. So it's really automating all the plumbing that you need to do for traffic. That's the whole point. So, still coming up. I'm going to switch to another demo system that I have here. Here's sometimes not fine with the demo system. So this is another demo system that I have here, which has these applications pre-created. So fine. And what I see here is that I have something called an app. So what it is a traffic coming in from an outside user. It's a service called photo, which then talks to other services like inventory and so on and so forth. So this picture is completely built in real time. So it's based on traffic as it's going through the system. And if I zoom into one of them, photos, for example, this actually shows me different metrics like latency, for example. This is the latency as seen by the user, and this is the latency as seen between photo and checkout, for example. I can also look at, for example, this service photo alone, and I can look at its end-to-end latency. So, for example, in this case, on an average, across all the requests that came in during this period, clients were about a millisecond away. It's all running in the lab. Server, again, about a millisecond away. Just took about a millisecond to respond. Data took about a millisecond to go down. Now, I can also zoom in to everything down to an individual request level. So in this case, for example, if they wanted to look at any individual request, so this is a request that came in from a client. It came in to this URL and it got this response and like that. So essentially, I can look at it as an application and all its constituent microservices. I can look at things like latency, throughput, errors across these services. I can zoom into a service. I can look at on an aggregate how this application is performing, how its points are performing, and I can also look at it individual requests. So at the end of the day, it allows you to create enterprise class applications, allows you to monitor them, allows you to troubleshoot them, and secure them. So as part of this, we provide a lot of security policies around TLS offload, things like WAF, and simple rating the target blacklist and whitelist. So that's I'll stop here and take any questions on how we how this works. And
All the metrics that you collect, where they're being persisted, that's remembering what you're doing. So all the metrics that you collect, are you storing those in Heapster or something else in the cluster, or are they short-term metrics only, and how long?
Yeah, good question. So we collect two types of information. The raw information consists of metrics and logs. Metrics are stored in a time series database on the controller. The real time that we collect, it's actually a second data point. It's stored up into 5 seconds. So we show. And then the non-real time, the smallest one is about a 5-minute roll-up. We also have 5-minute roll-up, 1 hour, 1 day roll-up. Depending on the granularity, we store up to a year, sometimes even more. The logs are actually collected on the data plane instances. And for the most part, they are stored on the data plane instances. Except when you actually want to see them, then we actually pull them over and index them for indexing them. And essentially show all these elements. Okay, all right. Thanks for being here. And I'm going to speak. Thank you.
Well, yeah, or uses, whichever you like.
Thank you. Next up, we have Sri, who will talk about Kubernetes on AWS.
Let's see your slides. Okay, It's gone. Can you see it now? Disable presentation mode. So something big one here, right? So something big one.
Are you mirroring your screens?
Alright. This is set. Yeah. So I'll keep it this way. All right. So the ski season in California this year was an awesome one, right? And it's amazing how skiing, the experience of skiing is similar to, in some sense, to the experience of running Kubernetes on AWS. When you think about it, you see it, it looks great, it looks beautiful. You think like this is going to be awesome. I'm going to get a lot out of this. So you can start. The first thing that you get introduced to is these complicated, cumbersome tools. Uncomfortable at times. But then you don't want to stop there. That's the beginning. So you kind of pull through it. You go through your lessons, your videos, your research, and at some point it's time for first flight. And then when it's time, when you actually run cluster, or when you go down the slide, or when you go down the slope, the first thing that happens is that you fall. At times when there'll be these sensational tumbles, and then you're really worried, something is wrong. What is it that I'm not doing right? But you know what the worst part of that is? You're down, you're out, if you look all around you and everyone is doing just fine, they have no problems whatsoever. They're seamless in the way they do everything, making you wonder what is it that I'm doing wrong. And then you start talking to people and everyone tells you the same thing that they tell you about anything else. If you keep trying, you get it. So anyway, hi everyone, my name is Sri Davekar. I am a software engineer at Athletics, and today we will talk about reliable, scalable Kubernetes on AWS. Let me tell you a little bit about what Athletics does. So we are building a platform for developing and running containerized applications in the cloud. And essentially, the mission of the company is to simplify the journey to cloud with three things. Infrastructure automation, so we make sure that we deploy your services in cloud, especially on AWS, and not just deploy the cluster and EC2 instances required for that, but several other services required for running Kubernetes, for running things, meaningful workloads on AWS. So all other AWS can also be provisioned via the platform. End-to-end DevOps workload, so it's not just that you're getting a cluster, you kind of get a full end-to-end DevOps system. We integrate with your source control and then make sure that you can run your CI/CD pipelines on top of this Kubernetes cluster. And governance. So when it comes to cloud, I think one of the biggest problems people have is visibility into what type of resources are they using. Who is using these resources? What are they doing with these? More importantly, how much am I paying for these resources? So an Athletics cluster, money is the first class issue. And you give deep visibility into which user or what workflow or what application is using how much money. And it's not just about visibility, you can actually take action. You can do things like, I only want to spend this much amount of money on this type of workload. So at some point, you start receiving some alerts, and then at some point, maybe if you exceed that budget, you can actually stop running, or the system will stop running that workload once you exceed a certain budget. And specifically about this meetup, or specifically about Kubernetes. So for the last year and a half, we have run anywhere from like several hundred to maybe thousands of Kubernetes clusters on AWS. A lot of them are dev clusters. Every developer has their own Kubernetes cluster. But we also run several production level workloads so as to kind of get that visibility into how is it that Kubernetes runs on AWS, what are the problems we see, and what have we done for these problems. So we're going to share, I'm going to share some of these insights today in this talk. So this is the outline. We'll talk a little bit about Kubernetes. Essentially, this is kind of like a sequential rundown of what are the problems we ran into when we started running Kubernetes on AWS. And not just running like small, tiny pod clusters, but trying to run a big cluster at scale and seeing what kind of problems we run. We ran into some fields. We ran into AWS rate limits, volume-related problems, several of them, cloud hygiene, so things like literally operationally, what is it that we can do, like in terms of operations, that can actually help us keep costs down and do better or make better use of AWS. And then we go on to scaling. So some of these things actually resulted in us thinking a lot deeper about how do we scale this cluster. The promise of cloud is to kind of give you these infinite resources that you can actually use. How can we actually make that happen? That's where auto-scaling groups come into play. All right, so let's get started. Kubernetes. So, after getting through that first initial hump of kind of setting up a cluster on AWS, we got that and we tried to just hammer it. Just run pods, run it for some time, kill those pods, and see what happens. It wasn't just running these pods themselves. These pods at times were like creating other resources such as persistent volumes and persistent volume claims on AWS and seeing what happens. And one of the first problems we ran into, especially when we ran like this cluster, this stress test for about a day or so, you will just see that the cluster is unresponsive at some point. And when we started digging deeper as to what is wrong, we found that the HCD component of this cluster was actually getting wounded. So what was wrong with this? Or if you take a step back, HCD is used for kind of storing all the configuration information about the entire cluster. It stores a lot of in-memory data. It has lots of snapshots about everything that's happening in your cluster. What pods are being generated? Who's generating them? What is the configuration of these pods? What are the nodes in the system? All the events happening in the system, all of it is very stored in HCD. So, and it has, HCD has this mechanism of actually putting a bunch of data moving it onto disk. But if you have a high amount of churn in the system, you just have too many events or too many things being shoved into HCD, and the data to write down to disk is lower, and at some point HCD is going to just keep on consuming your memory. Whatever memory provision, and it died. Not only did this affect HCD itself, there were other services running on Kubernetes master, such as the API server, key controller manager, which were kind of getting affected because of HCD. The HCD was down or slow, then these services got into some messed up state, and essentially the cluster was unusable. And what did we do about this? So I'm sure there are many other there must be other parameters we could have used, but looking at the documentation of HCD, one of the things they do tell you is that the number of snapshots is a known issue. The number of snapshots by default is something like 10,000. They recommend on their website that if you think that you don't need these many snapshots, tune it down, and you might be able to give your cluster that much more space for kind of these spikes where you have far too many events coming into HCD, and that gives you a little bit of leeway. So we tuned that parameter down, and since then, we've been able to run our clusters far longer without any problem. So the takeaway from this would not be that go and straight away look at this parameter, but the idea that it would be good to kind of figure out whether the HCD configuration in your cluster is actually enough for the workloads that you have. HCD provides some really interesting simple tools called etc DCPL, HCDCPL, which can be used for quickly, literally like a bash script that can quickly stress HCD, just write thousands of entries into it and see how the memory is going up or down, or things like that. AWS limits. So once we got past this HCD problem, we had a cluster that was running. We still wanted to run the same set of tests, stress test the system, see what happened. And we kind of went away from the Kubernetes side of things into AWS limits. So, believe it or not, AWS has limits. And the first limit that we ran into was rate limit. So any resource that you require from AWS requires you to make an API call. Instance, whether it is a volume, whether it is even getting the status of an instance and things like that. All of these require API calls, and these API calls have limits on them. So if you have a cluster which is like continuously going ahead and querying AWS for something, there are times when AWS returns an HTTP 500 error saying that you're requesting at too high a rate, and I'm not going to reply to this. One component where we ran into more often than not was this thing called the cluster autoscaler. The cluster autoscaler is this open source component that is used for like increasing and decreasing the number of EC2 instances in the cluster depending on the load. So it understands how much, what's the load on the Kubernetes cluster, how many outstanding pods are there, and based on that, it can provision new resources or provision new instances. But it queries autoscaling groups far too often, and at a certain frequency, started causing us causing rate limit problems. Autoscaler was one. The second one was just the rate at which you were creating EBS volume. So every time you have to make an API call to query an EBS, get an EBS volume, then go back to AWS and say, create tags for this, then go back to it and say that, is it really provisioned? And these kind of things started getting in the way. So we had to kind of, there were some parts which we could do ourselves. There's some parts in Kubernetes. For example, Kubernetes can provision volumes there for you directly on AWS. And at that time, we saw that Kubernetes can go to AWS, but at some point, if Kubernetes gets back errors, then it can get into some odd state, and you have to figure out what is the problem and what can you do about it. So API rate limits was one problem, but the other one was just the cap on number of resources. This might be a problem specific to our account because we had far too many clusters. All developers had their own cluster. Maybe several of them were kind of running these stress tests. So not exactly just to kind of check what maybe their own component, but because there were far too many people, far too many clusters, we ran into like the caps for pretty much everything. I mean, VPC, subnets, launch configuration, S3 buckets, iron put the name of that in any AWS and kind of sort of keep that in. Yes, AWS says that you can go back to them and ask them to bump up that limit, but even that has like some cap. So, for example, VPCs we thought was like ridiculously low, so like 20 VPCs or something. And we asked them to pump it up. They pumped it up to 50. But even that, like at some point, you're going to run out of them pretty soon. So, what did we do about this? I mean, and this is where kind of technology kind of is out of the window and it comes down to operations. What do you do as practice? So we just had to do things such as reduce use of resources, figure out what exactly do we need, how much is needed, do we really need every cluster to kind of stress test the system. Have multiple accounts, that's actually a good idea. I was at the AWS Summit last week, 2 weeks ago, and there was one company there who also talked about multiple accounts. AutoCAD. But they were talking about how they needed multiple accounts because they also ran into the caps of pretty much every single AWS resource they needed. Delete unused resources. Actually, this was good in some ways. It's just good not to be paying for resources that you don't need. So this made us kind of go back and delete everything that we don't need. The interesting thing that comes with deletion is what to delete. If you really know what to delete, you need to know what are the resources that maybe each cluster or each user or cluster needs. So we have to go and make sure that we are really tagging all resources correctly so that we can actually go ahead and delete them. Yes, and now comes the thing that kind of sort of caused us the most trouble. So I have a big asterisk sign there. It says under development because I think the Kubernetes community also acknowledged that the use of volumes and persistence for applications running on Kubernetes was an area under active development. So our testing has spanned for over a year, and Kubernetes has gone through several releases during this time. We started our testing mainly on 1.4.3, so Kubernetes version 1.4.3, and since then several things have been done to kind of make volumes and stateful services much better on Kubernetes. So some of these might have already been fixed as of like Kubernetes 1.6. Let me see, go ahead and tell you the kinds of issues we ran into. Might be something that you could experiment with in your own clusters to figure out if that is even a problem for you. So volumes got attached to wrong pods. So we had this interesting case where we had a Redis pod which needed its own volume, and we had a Kafka instance which had its own volume. At some point, these two pods were running on two different EC2 instances. These two instances went away because somebody deleted them or AWS deleted them or whatever. And the pods moved to two other instances. But when they moved to two other instances, the Redis pod got the volume for Kafka and Kafka got the volume for Redis. And at some point, we were like wondering, we stored a bunch of this data in Redis and I don't see it. Or there was a bunch of these things stored in Kafka and we don't see them. We kind of got over this by kind of working on our way around it, because when we reported this, we were told that yes, it's a known problem, we are fixing it. There is a very interesting notion in a very interesting use case for what are called init containers in Kubernetes, where you can basically run a container before your main container can run. So we ran an init container before these pods ran, and we made sure in the init container that the volume that is being provisioned for this pod is really the volume that it's supposed to be. So we had a volume, we had a tag called Redis, and the init container would check that is this really the Redis volume. If it is not, the init container will fail, and Kubernetes will fail at what itself. Failure to unmount and detach volume. So another interesting case related to movement of pods. So we had these pods running on some EC2 instances. At some point, the instance went away, and the pod moved to another instance, but the volume that was used by this pod did not move with that. So that old volume kept on, at least on AWS, kept on saying that it's attached to that old instance. And this pod, which was scheduled on another instance, kept on waiting for this volume to show up at some point. And just kept waiting on forever. There's no end to this. So we had to do something to kind of forcefully detach this volume from that instance. And then Kubernetes would do the right thing of moving this the volume towards that instance and run it from there. Runaway volumes because create and tag were two different API calls. So this I think has been fixed by AWS recently, I think a few weeks ago. But earlier, like you had to make two different API calls to AWS to kind of create a volume, to get back a volume ID, and then go back to AWS and take for my cluster name. But if in between that, if your pod or your service or your cluster crashed, you now had created this resource in AWS and you had no way of accounting for it. You did not even know that it was there, so you had no idea what it was for. And there were several times we ran into these problems. This had two problems. One is we land up paying more money than we shouldn't be. And secondly, we also, because of these kinds of things, we hit those caps, the limits on the number of volumes you have, which also cause other problems. Yes, and this was really interesting. So disclaimer, we've only seen this twice, but twice it has happened. We actually created a volume. AWS gave back a volume ID, but when we went back to use it, it said it was not there. We were wondering, like, how does that work? This might be a bug. We reported this, but at least I haven't heard back about whether this was I haven't heard acknowledgement this was a problem and it's been fixed. But we have actually a case for that here. So this is the CloudTrail log, and you can see here, like we created a volume and we sent an API call to create tags to this. These are two different API calls. They apparently went at around the same time, but you cannot call create tags without getting this volume ID. So we clearly made this API call first to create the volume, then we made this API call to create the tag. And these two succeeded. We started using this particular volume ID, volume dash 04. But then subsequently, if you look at this, all the attached volume calls kept on failing. And they failed because, and the error code given was volume invalid volume not found. We are like left with, like, what does that even mean? So since then, the fix is like every time you create a volume, make sure it's actually there. Like write something to it, read something from it, make sure it actually is there. If it exists, you spend those extra calls and extra APIs, verify it actually is there, and then you use it. Interesting case, but as I said, we've only seen this twice in like thousands of clusters. All right, so once we got past this, we had these problems, we went past this, and we kind of landed into an interesting problem, which was kind of related to both reliability and scalability. So in our case, we had these two kinds of pods. We had let's just say we had system pods and we had user pods. The system pods kind of, would sometimes start these user pods, they would get back their status. The system pods were required to be running all the time. The user pods might come and go. And there was this dependency or this difference in the priorities of these two pods, so to speak. But the underlying infrastructure on which they were running were all similar. Like this question. Right. No. I'm just saying that, logically speaking, we had two types of pods. I'll take credit for it, but yeah, so we had two types of pods. Logically speaking, two types of pods. And we needed, it was our requirement that the system pod should keep on running all the time, the user pods would come and go. But the underlying infrastructure on which they were running was just the same. The same set of EC2 instances. There was one auto-scaling group, which is what typically any Kubernetes installer, KOps, KubeOps, any of these things do. There's one auto-scaling group. In that one auto-scaling group, you have your instances, and all these pods run on those instances. At some point, what happened in our case was there were a few of these system pods. There were a bunch of these user pods, and there were another bunch of user pods waiting to be done. There were not enough resources, so these were pods waiting to be done. The nodes went down because, again, either we decided to do this, or maybe one of us deleted these nodes. The auto-scaling group brings back all the nodes that were previously running. It brought back all these nodes. When these nodes came back up, the Kubernetes master scheduled all user pods, the ones that were running previously as well as the ones which were waiting. But none of the system pods were actually running. None of the system pods now went back into pending state, waiting for resources. And we landed up in some soup where you had all these user pods running. They were actually, some of them completed, but the system pods that were kind of waiting to, read them were kind of not even there because they were just waiting to be done. Now, of course, there is scope here for us to improve the architecture of our system, which we did. But this made us think along these lines that if you have some sort of priority requirement, if you have some difference in the way your pods need to be scheduled, especially when they restart because your underlying infrastructure can go away. If you use one set of resources, then you can have a problem. So this made us think more about what we do. So if we have pods that have ordering requirements or priorities, it's hard to enforce any priorities when enforce any reordering guarantees when that happens. So this made us think about using multiple auto-scaling groups. So how does that help? So we created two auto-scaling groups, one for system pods, one for user pods. Kubernetes has this great notion called node labels. You give those nodes in the system auto-scaling group, you give them a label called system nodes. And the other auto-scaling group for user, you give them a label called user node. And when you run your pods, you kind of give this node selector, to kind of make these pods go to appropriate nodes. So now with multiple auto-scaling groups, you've actually divided the resources that you have into two groups for these pods to run for you. And with that, we were able to achieve the thing that we wanted. That even if the whole cluster went away, all the nodes went away, new ones came up, we'll still be able to make sure, guarantee that the system pods will always run. User pods can kind of compete in their own auto-scaling group, compete in their own set of resources. So that's what we did. We added labels to these nodes. We created multiple auto-scaling groups. We added correct labels to these nodes, and then we ran these pods with correct node selectors. And this actually became an even more fun project because once you separate auto-scaling groups, it actually has many other benefits. So once you have two different sets of auto-scaling groups, let's say again for system pod and user pod, and fundamentally you can think about it that you can actually scale them differently because that's what auto-scaling groups in AWS are. You can scale your user pods separately from your user nodes separately from your system nodes. You can literally do things like, okay, I'm going to schedule AWS user nodes far too frequently, but my system nodes can remain stable. You can do heterogeneous clusters. So each auto-scaling group has this notion of a launch configuration, which basically tells you what type of instances should run for that auto-scaling group. So you can imagine saying that, okay, my user nodes could be like T2 medium type of instances, smaller instances, but far more in numbers. So I'll probably scale out far too often. But my system pods would have a launch configuration which are of type say MP large, which means that I might have multiple or lesser number of system nodes, but I have bigger ones so that I can accommodate. I mean, the combinations you could mix and match depending on the kind of clusters you have, depending on the kind of importance you have to each type of. spot instances. Yeah, I would love to give a separate talk on spot instances. But you can, so cost is a fundamental problem again on AWS. And AWS, if you look at spot instance pricing, spot instances are, at least in my experience, especially in the US West region, spot instance pricing is roughly like 20% of what the on-demand nodes are. If you're paying, say, maybe you're going to pay 20% less money for those instances if you're okay with the relative instability that can come with it, that those instances could just go away at some point in time. But now if you have multiple autoscaling groups, you can decide to use spot instances only for one of these autoscaling groups. So you can totally imagine saying that, hey, my user pods are kind of, they're more in number and lesser in priority. So maybe I should use spot instances there. They could all go away at some point, but maybe I will restart at some point. Or maybe I can keep an eye on these on these user nodes, and if these nodes go away, I can spin up new ones on demand or whatever. But I can use spot instances only for some part of my system so that I keep my costs down. And the other parts, which are kind of maybe a little more important, I will keep them running using on-demand instances that are maybe more expensive, but also lesser in number, so I keep my costs down. So the thing that we spoke about, all these problems, these solutions, we actually put that in place. And I'm going to show you one small thing, especially to do with these autoscaling groups in an Athletics cluster. Not exactly as in just literally show them. So I have a cluster here. So this has 13 nodes right now. And you can see that there's one master and 12 million instances. And I have 3 autoscaling groups. So we have, you can see here one which is called A, which is kind of the one that the system one that I'm talking about. And we use the second one, which is this one. These are the one which is the user autoscaling group. We also kind of make sure that we tag them accordingly. We keep giving them a tag called X here. So this one, which has an X, and it has a X here called Athletics, which is where our system pods run. And this one, which is the variable, the user autoscaling group, has an X here called user. And then okay, and I'm just going to get a listing of the current pods that are running this. And I just described one of the pods that I'm currently running. And as you can see here, I have a node selector here which says that here should be applied. So, so this, simple. It's very simple to just add a new node selector whenever you're running pod, and that can actually fundamentally change the way you can scale your clusters. We have an interesting idea of about also scaling like throughout the whole. It's kind of a pyramid, right? You have like a master, then you have your system pods, and you have your user pods at the bottom. You can say that for every 3 user nodes that I add, I'm going to increase the number of system nodes by 1, and for every 4 such instances that I run, I'm going to increase the number of masters in the master autoscaling group by 1. Have a nice hierarchy of pods that are running in the system, or of the nodes that you have provisioned in the system. So, sorry. Yeah, that was mainly the kinds of problems that we ran into and the scalability issues that we kind of tackled so far. I'm sure there will be many more interesting ones. As I mentioned, I'm sure some of you are aware of this. Like the space is extremely fluid. Like things happen every day. Every day there's something new happening. Some new component being built, some new features being added. I'm sure things are getting more and more stable as we go along. So some of these things may not be a problem anymore, but it was just the idea that it'd be good to kind of know what problems others are trying to, so that it's something that you could test with. So this is the kind of, so just to go over the kind of problems that we ran into and what we did. We did have long running CD tests. We ran into AWS limits. We have volume issues, and then eventually we kind of now we are at a place where we have multiple autoscaling groups, all scaling independently, and therefore making our clusters much more stable. That's all I have in mind. I'll be happy to take questions.
Yeah, so there was a question on CIS system.
Yes.
So if folks are interested, there's a proposal for a global presentation. But there's a proposal open now in Kubernetes to do like a resource placement priority, so you can get differentiated priorities across your pods. And so if folks are interested in that concept, it's not the same thing as having a system within your pod, but you can say this pod has higher priority for scheduling or from other chain otherwise. So like, cool that you run that and cool that that's a useful feature for you. That's not an issue to do.
Oh, cool. That's great to know. Yes.
It looks like your system only works on AWS. Does that also work for GitHub, Azure, or any other like workspace?
So all the testing that I was talking to you about in this last year and a half has been on AWS. I can neither confirm nor deny that we'll be running on Google Cloud. Oh, in Google Cloud, this experience should be much smoother. Well, that'll be awesome.
Typically, when you launch
I see. So when you say Google, do you mean Google Compute or do you mean Google Kubernetes Engine? I see. Okay. Okay, that's great. We are more than happy to work on any system that is fundamentally mostly.
What tools do you use to deploy and manage the lifecycle of your cluster in AWS? Is it something custom or one of the open source?
So we started off with Kubernetes, which was developed by the Kubernetes contributors. But at some point, the kind of things that we wanted, we had to kind of take it, fork it out, and kind of build things, kind of diverge from it and add our own stuff on top of it. But having said that, I have tested Chaos, which is currently the recommended tool for deploying clusters, and that seems to work just fine. Again, that was something that we had to. So when we started, there was no upgrade. It wasn't possible to upgrade Kubernetes cluster using Kubernetes. They always mentioned that Chaos is this new tool that we are developing and we are building, and it's the one that's going to help you upgrade your cluster. So Chaos allows you to do upgrades even today. We have a separate command called upgrade. In fact, it's really cool. You can say upgrade, you can give it if you want to. So it's not just like latest and greatest, you can upgrade to different versions. So it allows for doing that, but we had to build our own because we kind of started way before Chaos was actually functioning. Yeah.
First, thanks for that presentation. Great talk. I was wondering, did you try creating like your AGC private subnet? Because from my experience, that I heard that Chaos is going to solve it.
We do use instances which are in our private subnet in our own VPC. I'm not familiar with whether Chaos will be able to help you with creating those in your own VPC. That part I'm not so sure. No, not really. So yeah, I'm sure when you tell people that I tested something 10 months ago, people are going to be like, "Oh, that thing has been done long time back." So, but I would recommend trying it out. If not, I'll be happy to try things out for you and let you know how things go. But we have deployed things in our own VPC, in our own subnet. All instances run in our own VPC. One more question, sir.
In all those things that are written, solely be built on top of AWS, or you have something in-house.
This is a good.
And also, all those things, especially for memory capacity, how do you deal with that?
Right. So autoscaling actually is pretty cool because Kubernetes itself has this notion of autoscaling. They call it what is called horizontal pod autoscaling. So you can actually configure Kubernetes to say that. Sorry, go ahead.
Actually, for a lot of big data and AI applications, not only for disk capacity, a lot of memory capacity,
Yeah.
as well as networking bandwidth issue. So that's why I'm asking you what kind of secret source in your auto capability.
So we currently rely on Kubernetes and Kubernetes to scale the cluster and AWS to scale things like at the infrastructure level. And as I was saying, like Kubernetes is horizontal pod auto scaling does exactly or it looks at exactly the kind of resources that we are talking about. So you can deploy an application and the Kubernetes master or services in Kubernetes can keep looking at this application, and if the memory usage exceeds, say, some configured number, say if it exceeds 80%, it will automatically create a new instance of this application and scale it up so that now you have two instances. There is a load balancer on top, so it will kind of now start distributing your load across these two different applications. It will scale up and scale down. So Kubernetes will do the job of scaling the number of pods you have. This cluster autoscaler, which again is an open source tool, it will look at how many pods are currently running in your cluster, what is the total memory and CPU limit that you need for running this much load, and if it looks at your autoscaling group and it sees that, hey, if you have far too many memory and CPU requirements and your current autoscaling group is not sufficient for that, it will bump up the number of instances that you're running in that autoscaling group. So new instance comes up. The AMIs used for running Kubernetes in AWS are such that the cluster membership is kind of automatic. These instances come up. They are kind of configured to know where the Kubernetes master is. So they come up, they'll automatically connect to the master and say that, hey, I'm a new million. These schedule pods on me. So it'll take some time, maybe a few minutes for the instance to come up. But once it's up, it's ready to receive these new pods. And these new pods will now start running on these new instances.
Yeah, it looks like a much more than however, it's still application aware.
AWS is not application aware. You're absolutely right.
Even it was not purely
Kubernetes is resource aware.
yeah,
Maybe that's the way to put it. Sure, but it's resource aware.
I had a product.
Okay. All right. Cool. Thank you, guys.
Next up at bat, let's see.
So next up, we have Tim from Google. He's going to talk about some of the RBAC features and Kubernetes
Are you the guy carrying the wooden tripod? Yeah. Oh, it's not wooden.
Still sharing my screen? No, right?
I don't think so.
Okay. All right, I was going to ask you, do I need to do something about it?
No, you can do the thing. You're fine. Thanks for asking.
Yeah, can you just try it again?
Yes.
What?
It's not.
more like a. I'll recognize it as a projector, but
It's great, great.
okay.
Idea for the face. But I'm not seeing it. Should I? Got it? Okay.
Are you sharing your screen? Monitor.
Taller. Press on.
All set up?
Yes, we are.
All right. Hi, sorry for bringing the next laptop. My name is Tim St. Clair, one of them. I'm the Google one. I work on Kubernetes and Google Container Engine. Sorry? Oh, sorry.
Well, I think you do.
No, it just needs to be higher.
Is that, can you hear that?
He's
better?
very good. Yes.
Okay, sorry. Yeah, Kubernetes Google Container Engine. I work on a lot on the node software and also security. And I'm here to tell you about one of, or if not the most important security feature in Kubernetes 1.6, and that is role-based access control. So before I get into that, if there's anyone who's new to Kubernetes here, this is how it works. Actually, the only part that I really want to make sure everyone understands is that the API server is the central communication hub for the cluster. And so whether it's a user request or a system request, if it's going through the CLI, the UI, or the REST API, it's all talking to the API server first. And so from a security perspective, this means we can focus on protecting that API at that point. So how do we do that? Actually, before we say how we do that, I just want to make sure it's obvious to everyone why we do that. I think the obvious reason is that the API is the keys to the kingdom. If you control the API, you control the cluster. Maybe less obvious is within your own team, maybe, even if you trust all of your developers, you can use better access control to protect against mistakes. So if your test engineer accidentally types the wrong command and tries to delete your production services, if they don't have the permissions to do that, then that can prevent potentially catastrophic mistake there. Another reason is defense in depth. So if you have a vulnerable service running and it gets compromised, if that service doesn't have full access to the API, then maybe your service is compromised, but your database isn't exposed. So anyhow, back to how we do this. There's sort of 3 steps in accepting a request in Kubernetes. The first is authentication. This is given some credentials or how you identify a user and make sure that they are who they say they are. All of these different systems that I'm talking about are pluggable. And so there's a few different options. Oh, sorry, this is, we can think of this as a function of a request to a user. So one option is just username and password. There's also token-based authentication where the client and the API server both know a secret token. And client certificate-based authentication, which is a little stronger because it's harder to man in the middle and steal those credentials since it's a public-private key. And we can also use a webhook, which is just delegating out to some third-party system as long as it implements the web API. So that's identifying the user. Once we've passed authentication, we now have basically a username within the system, and a few other attributes, but we have our user. So the next thing to ask is this user allowed to do whatever they're requesting to do? And this we can think of as a function of a user, a namespace, if it's a namespace resource, a resource type, end of verb, what you're trying to do. Accept or reject the request decision. Some different examples are allow all is just, if the user is authenticated, then yep, they can do it. The most basic. Obviously, we'd like to be a little stronger than that. We can use a webhook to delegate to a third-party system. This is actually how Google Container Engine integrates with the GCP IAM. And we have ADAP, or access-based, attribute-based access control. Prior to 1.6, and probably for some deployments still, this was the default. And this gives us a lot more than allow all. This lets us say, basically that mapping, specify it in a file. So a user, a namespace, maybe I, Tim, am allowed to do anything to any resource in the namespace, Tim namespace. The admin has full control of the cluster. So this is pretty good. But it has a problem, which is we're specifying this through a static file. That means that prior to the cluster coming out, I have to know everyone who's going to be accessing it, everything that's going to be running in it. You could potentially change the file, reboot the API server, or something like that. That's pretty clunky. And so what happens is you just end up saying, everything running in the cluster has full access, and that way when we add a new service, it will just work. Enter RBAC, or role-based access control. Don't worry about the role versus the attributes so much. The really important difference with role-based access control is the permissions are now a first-level API concept. It's an API object managed through Kubernetes, and this means that I can add and delete roles as I add and delete services, as I add and delete users, and I can make all sorts of generalizations around it. So one example of how this might be useful is we have two teams sharing a cluster, running different services. Team 1 needs to be able to have full control to manage the services running in the Team 1 namespace, but I don't necessarily want them accidentally mucking with Team 2 namespace services. That's the type of thing that we can set up pretty easily with RBAC. So let's start talking about, how this works. So the role, we can think of kind of what we had specified before in ABAC. That's now going to be our role in RBAC. So the role specifies the permissions, essentially. So as an example, we could say in Team 1 namespace, we want to create this pod service reader. This role has permission to do some read operations, get and list on pods and services. And so that's specifying the role. And now I need to somehow say that Tim, the user, is going to have the permissions of this role. And for that, we use a role binding. So the role binding is basically binding the role to the user Tim. And again, an API object in the namespace, Team 1 namespace. We say the subject is a user Tim. This could be also groups or service accounts or various other things. And the role reference is the role that we're going to bind to that user. And so now that we have the role binding of the role, Tim, the user, is allowed to make the get and list requests on pods and services in that namespace. The cluster role is basically a role without a namespace, is the simple explanation of that. So if we wanted to grant a user permission to get and list all pods and services in the cluster, we would use a cluster role for that. Now, a cluster role with a cluster role binding is that totally unnamespace version. We can also use a cluster role with a role binding. And in that case, we're using the namespace from the role binding to basically scope down the cluster role through that namespace. One point I skipped over is that the permissions in RBAC are additive only. This means that by default, any user has 0 permissions. And with RBAC, we specify the additional permissions that we're granting. So we're never removing permissions, we're only granting additional permissions. And this makes it a lot easier to, say, bind a user to multiple different roles, and in which case they're getting a union of all those permissions. So before I get to my demo, just the last piece of this pipeline is only for write requests. And this is the admission plugins. The admission plugins are, we can think of it as a mapping from the API object itself in the request to a potentially modified API object, and again, the accept reject decision. And this lets us do more advanced decisions based on fields within the API object. So things like, am I allowed to create a pod with a host path volume? Or making quota decisions, limiting on secrets. The image policy lets us specify which container images we're allowed to use. And we have a lot of other admission controllers that are getting added all the time. I'm not going to go into too much more detail there. Just know that exists. So I'd like to jump into the demo now. If you would like to try this out for yourself after the talk, my colleague Jacob Simpson wrote this great demo, and what I'm going to show is pretty closely follows that, and so that URL will tell you how to get through the setup and walk you through the steps. But I've already done the setup, and so I have here a Google Container Engine cluster running. Oops, sorry. There we go. Running 1.6.2, the latest version supported there. And I've set it up with RBAC, disabled ABAC, and I've added 3 users here. So what you're seeing here is the admin, and I also have a user Tim and a user Phoebe that I'll be switching through. I've used a little trick to do this. I've actually aliased kubectl to use a token bound to each user. So we're using that token-based authentication. Okay, so for starters, we have this new user, Tim. Tim was just added. He has authentication, but we haven't added any roles for him. So if Tim tries to get pods in Tim's namespace, we are forbidden from doing so. So as the admin, it's our job to set up Tim with the correct roles. So first thing we're going to do is this, can people in the back see this okay, or should I increase the font? All right, so the first thing we're going to do is create a role for Tim. So we say, we'll call it Tim's role, and we want to allow a bunch of different operations within the namespace. We'll say get, list, watch, some read requests, and create and delete. And let's say a bunch of common resources, pods, services, deployments, replica sets. It's wrapping, but the namespace is in Tim's namespace. So let's go ahead and do that. All right, we have the role. So let's go back to Tim and get those pods. We forgot something. We created the role, but we haven't actually bound it to Tim. So remember, we need that role binding. So we'll create the role binding, give it some name. The role is the role we just created, Tim's role. Same namespace. And this user variable is just the email address that I created for that user. So now we have a role, it is bound, and if we go back to Tim, we can get some pods. That's great. we can delete some pods. Success, that pod is gone, and our replica set recreated it. Okay, so let's see, let's step that down, sorry. Okay, so we have another user, Phoebe, and I've already gone ahead and created the roles and role bindings for Phoebe, same as Tim. And if we jump over to that user, you can see Phoebe can get the pods running in Phoebe's namespace. But suppose Phoebe wants to see what Tim's up to. Phoebe is not allowed to get access to, we haven't granted Phoebe access to anything in Tim's namespace. So let's suppose we want to do that. Now we could create a new role that was basically the same as the previous roles, but remove the create and delete request because we only want read-only access. But instead, we're going to reuse one of the default roles that's built in. So if we go back to the admin, and so we're going to use the view cluster role. And so this is a role, cluster role that's shipped with most deployments. Ignore the metadata. That's just stuff that gets added onto every object. We can see this is actually a much more complete version than the demo role that I specified earlier. We have basically almost every resource, excluding secrets and a few other sensitive things. And these are all read-only operations, get list watch on all these resources. So let's go ahead and bind that. So again, we're going to create a role binding. Create a role binding in Tim's namespace, but for Phoebe, and we're going to use the cluster role view. Now if I go back to Phoebe, I can get pods in Tim's namespace. And if I try and delete them, that's forbidden, as we would expect. So I just want to go back to some of those default cluster roles that the system ships with. A few of the cluster roles, I've hit in a few for now. We'll come back to this. But cluster admin, we can think of as root in a cluster. This grants everything. If you have cluster admin, will do it. Admin is similar, but it's intended to be namespaced. So you might bind, use the admin cluster role with a namespace role binding to say, this is the administrator of this namespace. Basically, they have write access to almost everything in the namespace. They can create new roles and role bindings within that, but not cluster roles and role bindings. Edit is similar. Read and write access to a namespace, or you could bind it for the whole cluster, but it forbids creating new roles and role bindings. And then view, we already saw, is the view-only version. Kubernetes API admin is a legacy thing we can more now. So now let's look at those system roles. So there's quite a few. And actually, these are all of the roles that are created for all of the different system components. So you might remember earlier I talked about defense in depth. And this is kind of what we're doing here. We're preventing any of the system components that might get compromised or might have a bug or have gone awry from doing things that they shouldn't be doing. And so there's a role for just about every component in that ships as Kubernetes by default. And we're going to take a closer look at that node proxy there. So yeah, you can ignore the metadata for now. So kubeproxy, for those who don't know, is responsible for setting up the routes on nodes. There's a pod that runs on every node for services and endpoints and nodes, routing traffic to the right IPs to find those. And so kubeproxy needs to be able to read or list and watch the endpoints and services. It needs to be able to get the nodes. And then there's also write access for events. This is just for tracking what the kubeproxy is doing and printing out some debug events if something goes wrong. Similarly, there's a role binding for this. It's just, like we saw before, there's a reference to the cluster role for kubeproxy, node proxy, system node proxy. And then we say is the user, and this is the system kubeproxy user that we set up for kubeproxy. Yeah, so that's what I prepared for today. Any questions?
Service.
Sure.
Can you repeat that question?
Yeah, so the question was about service accounts. So we can think of a service account as just a user account that's created for a non-human user. So in Kubernetes, every namespace has a default service account. So we can see there's a bunch of, oops. Yeah, so we have a default service account for the default namespace, for a kube public namespace, for a kube system namespace. And then within the kube system namespace, we have one for each component. And then these two user namespaces that I created through the npm namespace both have a default service account. You can also create a service account, a custom service account. So maybe you have 3 different services sharing a namespace. You can create a different service account for each one. And that's specified when you create the workload. You can say which service account that workload should be running in, and then use that as the user when you're binding your roles. Yeah. So having finer grain. Yeah. So service account again. That's the authentication step basically. So because that's separated from the authorization step, then we can simply say, okay, we have this service account user authenticated. Now, any of those authorization mechanisms that I mentioned can be applied to that service account.
At the beginning, you ran a script to refresh your cookie, and I noticed that there was no red error in that. Do you similarly have a way of avoiding that?
Yeah, so behind the scenes, that script is just running a gcloud command. Actually, if you take a look at the demo I linked, and maybe we can send out a link to that later. But one of the early steps in that demo is to disable the regular authentication mechanism that is set up for Google Container Engine, and say, actually, we're not going to use the webhook authentication. Instead, I'm going to use these manually curated tokens so that I can do the magic of the different users.
if you have an existing cluster and you're looking at moving more services to an RVAC enabled cluster, do you know of any tools that allow you to look at the actions occurring in the cluster so you can set appropriate goals for deployed services?
That's a great question. I don't know the answer to that, but certainly someone should write down the thing.
It's on recording. We'll hold you to it. And have a deadline by which you'll furnish an answer by email.
I will say that for 1.7, we're working on a lot of improvements to our audit logging, and that's something that you could use to see every request that a service is making.
In this case, I have to say restricted scaling for a node with labeled option, for example.
So if we go back, yeah, so remember I said that for authorization, we can think of it as a mapping of user, namespace, object, and verb to this accept, reject decision. What that means is that basically, if you're trying to do something that's not encapsulated in those 4 variables, then you're not going to be able to do it with RBAC alone. So for something like that, you would actually want to use an admission controller and look at the more specific thing, like, sorry, I can't remember the exact example, but you have full access to everything in the system then, and you can make that decision. And then you can use RBAC to say that a specific user should use that admission controller, admission controller setup. And that's actually how the pod security policy works. You have these different pod security policies, and you use RBAC to basically bind users to a specific, or say that they can use a specific pod security policy.
So the admission is only before, right? I could see that
so I said that. I'm actually not positive that's true. That's mostly how it's used. I'd have to double check that it's only used, that it doesn't apply to roots. I don't know if anyone.
generally they don't have, like, you don't have to do it. So like, you're trying to close an individual field and an individual object. You can't do that. But the mission controllers, you write them, you have to recompile a few to get them in. And so like that's a bit of a barrier to entry. But if the use case is really common, then like, I'm more than happy to review it as a general thing to get in the project. So but yeah, we lack field level access control, but there's some stuff. Yeah. The person who sits next to me couldn't answer that question. He's not here, but I my office.
Our roadmap is
here. But like that, you know, go to like a sig off and bring that up with use case, and I'm sure they'll tell you, yeah, we talked about field level access control. Jordan or get this channel control stuff.
We have a pretty long roadmap, so a lot of the times the answer is it's on the roadmap.
I see an asterisk in there. Is that a special little stream, or do fields support logging?
Yeah, so in ADEC, fields do support logging. In RBAC, I believe so, but only as the last character. Yeah. Yeah. Yeah, so the question was, if I want to be more granular, basically, than just performing, blocking operations on pods or accepting operations on pods, and say a tagged pod or a specific pod, can you do that? So actually, there are a few pieces that I left out of this. You can name specific resources here. And so that's by resource name. In Kubernetes, rather than tag, we have labels as kind of the general selector. And you cannot currently set permissions by label, but that's, again, something that we're looking at doing in the future.
Yeah, does RBAC integrate natively with the PBUI yet, or is that on the roadmap? So
I don't know the answer to that question.
So what is the persistence for the policies that are defined?
So all of the Kubernetes API objects are stored in etcd behind the scenes, and RBAC is the same.
And also in one of the examples, you showed that you have the verb and the result. So do you have to literally list all the verbs and associated resources, or is it one mapping that I can just find and club it together?
Yeah, so there is that kind of wild card. I can say, if I want to grant full access to pods, I can use, I can use a wildcard character there to say, all verbs are accepted.
Also, it's not how to conduct some policies. There are some policies that presumably provide out of the box. Say 1.7 or 1.8 is define new policies. No policies that preserve that thing.
So this is going to depend on the deployment. Whatever mechanism you're using to deploy might configure these things differently. I can say at least in Google Container Engine, we are very careful to preserve backwards compatibility. I think this is true for most of the default mechanisms. In fact, that's why you have to provide a special flag to disable ABAC in order to make full use of RBAC, because we have to keep that around for backwards compatibility. Are we doing okay on time?
So how much more secure Kubernetes than its underlying infrastructure like Google Cloud? As far as I know, Google Cloud itself is very easy to have, especially when your Unix is plausible, not API or CLI.
So we do a lot for security in Google Cloud and in Kubernetes. It's going to depend on a lot on your specific use case and if you've actually set it up in a secure way. We're investing a lot right now in improving our defaults, making the default distribution more secure. It gets pretty tricky because of what I was just talking about, which is this backwards compatibility.
But for sure, it's very good to go to DG Cloud. This is a lot of stuff. If launch the VM or whatever, you can, it's very good to scan the slash CD message. You can see text from facial, from content, it's very good to see. So they try to manipulate something. It's very annoying. And a lot of times, you may not be able to use API or CLI. It really doesn't matter whether you want to.
I'm not sure what's exactly you're referring to. It sounds like It sounds like something that could be fixed with better firewall configuration.
I just said, someone from somewhere, you try to create something, maybe you can't fulfill.
Yeah, let's talk after this. I think we're just about out of time here. So, but I'm going to stick around afterwards, so if anyone wants to ask me more questions.
Oh, wow. There's more.
Yes, get the lapel mic, yes, the lavalier.
We have a mouse in the house, and every so often it's cute.
Where did they go?
Yeah.
Anybody hear me?
Yes.
All right. Excellent. I'm going to get through the slides really quickly and get. All right. So I work at Red Hat on the OpenShift team, well, actually upstream Kubernetes team in service to OpenShift, which is Red Hat product based on Kubernetes. So I'm going to go through really quickly some. It seems like everybody here knows pretty much how Kubernetes is designed, but before the foundation. I'm going to talk about resources and controllers, just how they're formatted and how they're very extensible and how you can make your own controllers and resources and stack them on top of Kubernetes, and that works really well. I'm going to talk about deployments, not the other two because it seems like everyone's good for what they are, but I'm going to talk about deployments in that's kind of the top level abstraction for Kubernetes, and then I'm going to talk about the OpenShift extensions with Kubernetes and what role they play in closing the gap between developers and the top level of Kubernetes. And then I'm going to be good. So about me, I'm going to skip it. Running a long time, but yes. So this is a disclaimer. Okay. So the OpenShift has a lot of really cool features. Only one area of which I'm going to discuss today, which basically talks about the build workflow in OpenShift. But if you want to learn more, the documentation is excellent, and there's a YouTube channel that has a lot of demonstrations on how you can use OpenShift. Okay. Is that better? Hello? Okay. So Kubernetes essentially consists of two fundamental components. One is resources, which is the data or the spec files, YAML files, right? That store information about how the cluster should be, like the desired state. And then the other part are the controllers, which are the ones that read the spec files and then try to actually make the actual cluster
realize the desired state. So controllers try to converge the desired state specified in the resources. And this is a very simple design that is that you can really expand on. There's almost no operation that you can't realize using this model. So all resources in Kubernetes have what's called object metadata, and these are the fields. It has an API version, what kind of resource it is, a name that must be unique within the kind, and then labels which are used to select the resource. And so that object metadata is common across all resource types. It's just a foundation, and those are also powerful primitives in that you can take all this and create kind of arbitrary structures for your controllers to select them and things like that. So I'm going to talk about deployments. Most people are probably familiar with deployments, but they were influenced heavily by deployment configs, which I'll talk about later with OpenShift resource. And it contains a pod template, and it creates a replica set for every generation of the deployment, which can be thought of as versions of your application. So it creates a replica set, which creates the pods. Then if you change the deployment config, the most common, or change the deployment, and the most common reason you would change the deployment is to update the image that the deployment refers to, then it creates a new replica set for the new version of your application, and then depending on the deployment, transitions your application from one version to the next. And then once the replica set has scaled to 0 on the old version, you can kind of change that up, but that's good. This is an example of something that's really small. Okay. That's a deployment. I didn't do that. Okay, so this is basically how Kubernetes sets up. Where you have a deployment pointing to a replica set, or two replica sets in the middle of the transition, and then the pods is the replica set that's managing. So there's a gap there in that developers work in terms of source code, and Kubernetes works in terms at its highest level in terms of container images. So you have this situation, right, where developers have source code, and to produce the image, and then the image can go into Kubernetes, right? And that magic varies widely. Lots of people do yourself stuff, but try to create a process around it, maybe some tooling, some scripts, and stuff like that, to hopefully create some sort of reliable way of producing their application. This is where OpenShift comes in. So OpenShift stacks some additional components on top of Kubernetes to bridge this gap, where OpenShift has source code level knowledge of and can build your images for you. So build configs are kind of the central resource for the OpenShift build system. It supports several build strategies, which can range from, I have got this repository, and in the base of the repository, there's a Docker file that tells you exactly how to build it, and it will build your image for you. It can also do what's called a source build strategy, where it will detect the language or runtime that your application is written in, and use what's called an S2I, source to image build, to produce the output image. But the cool thing is that there's also triggers in this, so you can be triggered by GitHub webhooks, image change events, which also tie into source to image. So these are the build strategies that are supported. You can use a Docker file that is in your repository somewhere. You can use a source strategy where you use an S2I image as a scaffolding to basically as a scaffold image. Your source gets inserted, it gets compiled, and the dependencies get pulled down, whatever, such that it can run as an application. The resulting image is then tagged and pushed as a base image for your application. The Jenkins pipeline strategy actually allows an external Jenkins job to do the build, which is really flexible, and I'll show that. And then you can also use a custom strategy, which you use custom image to basically a fully custom pipeline. So with source to image, you've got these images that are language or runtime specific, and contain the runtime and build tools for your particular image. And it's fairly simple in design. You create this, you can create this image, and then you provide an assemble script, which in many cases is a bash script that compiles your source or runs your package manager to download the dependencies or whatever needs to be done. But at the end of that assemble script, when it takes it with a zero recurring code, that image is tagged, and that's the URL. And then run is basically going to be entry point for that. So that's the script that will be run in your application after you started. The S2I images that we support upstream. So these are the kind of languages and runtimes that we have S2I images for. And you can look at those as you can import those as a template and adapt those to your own needs, or just use those as already. Yes. All right. So image streams is another one of the components that's built on top of Kubernetes that was in a diagram I was showing earlier. And basically, it mirrors your registry state enough such that deployment configs and build configs can watch if something in the registry changes, and then trigger events based on those things. So in the case of build configs, if your S2I image changes, there's a trigger in the build config that will say, okay, oh, the image I was based on changed, so I can rebuild the application. And with deployment configs, if a build config creates a new version of your application, then the deployment config triggers off of that and then automatically redeploy your application. And then deployment configs are a lot like deployments. The reason was because deployments were based on deployment configs. They existed in OpenShift first. We still keep deployment configs around because because our deployment configs can watch the image streams and automatically redeploy when the image updates. So there's no ability for Kubernetes deployments to do that yet. But we're working on rebasing on deployments just to lessen the load of things we're having to carry outside. So let's see what we got. So what we have here, I'm going to start. Check my screen. Sure. Okay. So just to kind of show you where OpenShift starts, the command line, the command line client is called OC. So you can do OC get namespaces, for example, and get the namespaces. Now, if I just to show that a lot of people into OpenShift is like a large, maintained separately from Kubernetes, and that's not true. If I dump the API, if I dump the endpoint here, you can see all this. This is all Kubernetes. These are all the Kubernetes endpoints, right? Only down here is it different. This is the OpenShift API, and it's a separate endpoint here. So if I so these are all of the resource types that OpenShift puts on top. Now I'm going to be talking about 3 of these, so you can see where this is going. You might also notice that there's cluster role bindings and users and role bindings and OAuth clients and stuff like that. That's because OpenShift has had an RBAC system from the very beginning, because OpenShift is a multi-tenant environment, and so that's a basic requirement for what OpenShift was.
We found that everything that you just saw was largely aligned with that, and our intent is to now that once the traffic.
Yes, yes.
If you look at the primitives, they're literally the same thing.
So this is the OpenShift web console. So I'm just going to start where we want to start. So this is, I started up a box in Patty.net, and I ran OC cluster up, which is the client. And it starts to get a all-in-one containerized OpenShift instance, and that's actually what's running. So all this demo will be happening on that one machine, is produced by one command. So I'll create a demo project. The first thing I'm going to do is I'm going to start. So these are all templates that come preloaded in OpenShift.
So just I'm going to deploy one of these in a minute, but I'm going to start this right here because I'm going to do Genius pipeline later. It takes Genius a little while to set up. So I'm going to start that now. So this is a template, and this is how the web UI renders it. Basically, these are all fields that you can fill in that will be, rendered into the template with the YAML files that make up the template. So all of these work pretty well out of the box. So I'm just going to create. You can see that Human Services is creating your project. It creates quite a number of services. If I go back here, you can see the deployments are running. It's created 2 services here. You have the Genius deployment config, and then this is this is most analogous to Kubernetes ingress, but we take it all the way to the end. Ingress is just it basically contains data about how you can make a load balancer. We have a load balancer. So, and this resource is called a route. So when that comes up, that'll work. So this thing, while that's coming up, I was wanting to show. Here's the RBAC interface for OpenShift. So this is my user, and I'm the admin in this project because I created it. You can also see the service accounts that exist. When I started the Jenkins template, for example, I created this demo Jenkins user, which has edit access on projects. And so from here, you can edit new OpenShift and create a new demo user, and you got the roles here that you can assign to the user. And so, and actually, these are the usual roles. There's actually many roles, so it's fairly granular. So our Jenkins instance is up now. When you bring up the Jenkins template, it integrates authentication with OpenShift. You can actually log in with OpenShift credentials really far. So the next thing I'm going to do is I'm going to run through the entire workflow. So this is the OpenShift Node.js example application. So I'm going to fork this just so that I can push to it later and trigger the webhook so I can show the whole pipeline running. Okay, now that's there. The next thing I'm going to do is add that to OpenShift. So if the runtime is JavaScript, Node.js version 4, okay. And this is the example that I'm going to use my own. And I'll create that. So when you go in here, you can see that a build is running. And if we go in here, you can actually drop into what's called the Origin SPI builder and see what's going on. So it has it's pulled down my repository. You can see the latest commit. It's injected that into my SPI builder, and now it's running npm to pull down all the dependent packages. After that, the assemble script that I mentioned earlier exits with 0, and it pushes it to the OpenShift internal registry. And when it does that, the image stream gets updated. The deployment config is watching the image stream, so it has already gone and deployed the image. So I've got one file here, and I'll click on the application. It's an OpenShift application. And then you can scale that up however you want. So, I want to go through the if I go into the build, go in and see the YAML, just to show kind of how this is. So this looks a lot like a Kubernetes YAML file, right? You have your object metadata all here with labels and all the normal things you can see. So here's something you can have various trigger types, and you can have any number of them. So there's a generic webhook, a GitHub webhook, and then there's also a trigger on image change. And it's watching this this was the last ID that it deployed, but it's watching an image stream before it changes. And so, and then if I change the config itself, it will rebuild. Git repo that it's pulling the source down and injecting into the builder. And here, the source is a type source. It's building with an SUI image. And the SUI image is coming from an stream, and it's Node.js before. Now, the cool thing about this is that it registers a trigger on this SUI image. And so if you find out, oh, Node has a vulnerability or something like that, right? You rebuild your SUI image, and you're like, oh, now I need to rebuild all of my Node applications to pull in this new runtime. That actually happens automatically because the build config is watching this SUI image, and so all of your applications rebuild as a side effect. And then as long as you scale it out enough, the deployments roll out, so your application never goes down using the standard Kubernetes. All right. So, and then deployment configs look all very much like upstream deployments, except for the triggers section, which was similar to the build config, and it triggers on image change or config change. So, all right. Let's go ahead and try to do that. So if I go into builds and go into pipelines, so this is where you can create a Jenkins pipeline that will do, like, it's got an OpenShift plugin that allows you to call into, say, build this build config, deploy this deployment config, but you can control exactly when that happens. And you can run tests and stuff like that. If it fails, then it blocks the build config or it blocks the deployment. Promote your images through different projects and tests and staging and stuff like that. So I've got a pipeline YAML here. And so this has a trigger of its own here. It's going to have a webhook that I can register with GitHub. And then here's my Jenkins pipeline. This is the most basic of pipelines. Basically, it's doing exactly what the source strategy would do. It's doing the OpenShift build. It's doing it against this build config. And then if that is successful, then it will trigger the deployment. So if I create that, so there's a few things I need to do real quick to the build config. Right now it's designed to, it's configured to automatically deploy things, but that's not what I want to do anymore. I want to let the Jenkins pipeline take care of that. Here. All right, so we've got our pipeline here now, and we don't have any runs on it yet, so we can hit start pipeline, and that basically manually triggers this build and deployment process. So I'm going to go into GitHub. So this is my for example example program. Nice. All right. So this is the webhook URL. I kind of save this off to the side. For deployment configs and build configs, this is generated for you, but pipelines, the UI is building custom pipelines, and the UI is looking at them. So, but this is the secret that I put in that YAML file in the pipeline. So it's on, we have a self-signed cert, so we disable self verification at the webhook and check. Wow. Awesome. All right, so the endpoint is responding. It's great.
So this is our application. So what we should see here is if I commit something to this, let's change something that's obvious. Check. So this is basically the header you see at the top of that page. So go ahead. With that. And if you go over to the web console, there, so you can see the pipeline that started executing. And it's going through the stages that I defined in that Jenkins file, right? So if we do view log, it will dump us into the Jenkins job that's running. You can see that this is similar to the source and image output that we were looking at before. You can see my commit here, right? More awesome. Pull down to the top, the head of my master branch. And the layers are pushing. Now if we go back, you can see build image, now it's redeploying. You can see the transition from the old deployment to the new one. And after basically the old replica set goes to 0, deploy application will complete, the pipeline will be done. So that's all of the demo. You can go in here and see how the pipeline went, and it actually tracks pipeline completion time across builds, and so you can see like if a commit along the way kind of dramatically increased the amount of time it takes to build an image or the size of the image and things like that. So it's all very cool. So really all you need to do what I just did is to download the client tools from the latest stable origin release and then run the command cluster up. And that if you have that Docker installed, but when it does that, it brings up the container environment. Play around with that right there. So are there any questions?
Wait. The magic wand.
So OC cluster up does a really good job. The Ansible stuff I've looked at, but is it pretty reliable to deploy origin on standard Kubernetes cluster? Because I know there's problems with that. Yeah, so the standard cluster, let's say GPU or super props or whatever.
I was the one who wrote that, and
So it's always been a goal of ours to support layering OpenShift on top of existing clusters. In the beginning, that was possible, and in the present, we've discovered some complexities to do that, and so we have a lot of Red Hat employees going to make generic machinery and stuff inside of Q, and we probably didn't know that in Q16 for having a ton of units to support that. But generally speaking, right now we don't yet support that as a targeted deployment, but we want to get to that point, and it's a goal that we're just making. Like, so generally speaking, like there's a lot of interest in the community around third-party resources, and there's a lot of Red Hat customers that also want to take advantage of third-party resources. Practically speaking, when you're developing a product of this complexity, you don't want to build it on third-party resources, and you want to have a little more strict behaviors on cross-version schema type things that third-party resources won't do. So we want to be able to support layered API server patterns, and so while doing now around service catalog, and I know Morgan's here, he was here, we're using that as the proving ground for a lot of stuff, which is supposed to be like the first project in the ecosystem that's trying to layer on top of Cube, using either third-party resources of the storage type or what we're calling user API servers. And so, at least at Red Hat, we're investing in service catalog to prove out these options so that we can, in the future, obviously, do it. But right now, again, you want to keep us.
One wishes to touch the magic wand.
Ah.
Peter, finish.
I'm not a big fan of PaaS, but I'm just curious, do you have any sort of benchmark against the cloud foundry in terms of usability, performance, and cost?
No.
It sounds like you didn't clarify though, just that everything you saw there was just running as a pod on the cluster. So, yeah. Yeah, no, I'm not. Yeah, I'm not going to go into that. But, yeah, he's not privileged to do that either. Yes.
The magic wand has its limit.
Well, thank you all very much.
Well, thanks, everyone for coming.
That's nice. That's nice.
Thank you, everyone.
Great. Thanks so much, everyone, for coming. Feel free to stick around for about half an hour just to socialize and chat.
There might even be pizza left.
There might be pizza.
Okay.